questions to me? Okay. So what we discussed, we ended up discussing last time is Lightroom quantization of open closed strings, and we kind of tried to classify what consistent string series we have. And so now we completely change the gears, and what we're going to study for probably the next 2 lectures are conformal field series. Okay. So I see it. Well, for the string theory, what's relevant is that once we fix the diffeomorphism invariance on string roll sheet, so for string theory, once we fix roll sheet diffeomorphism invariance plus while invariance in a covariant form, then what we will be left with, we will be left exactly with the CFT. So we will be left with the CFT on the roll sheet. And so if you wish, that's a motivation from the string theory perspective. Why do you want to study conformal field series? But there is more motivation, which I think is much broader than that, and that's so what's CFT? So conformal stands for a new type of symmetry transformation, which we will discuss extensively. And so in particular, so one of the generators of the conformal symmetry group is a generator in which if I have a coordinate x and I rescale it by some constant, so there is a, I'm going to use same notation as I'm going to do later. So zeta is a rescaling of spatial coordinates, and so the series invariant under conformal transformation will be invariant under scaling, right? So a scaling transformation is part of conformal group. So in particular, if you're talking about series which are invariant under conformal transformations, they will be invariant under scalings. And those are the series that happen very often in condensed matter systems. So CFTs, so the comment I want to make here is CFTs show up in condensed matter. At typically second order phase transition. So when we talk about phase transitions, exactly at the transition point, the dynamics is scale invariant and is described by a CFT. They can shows up in condensed matter at second order phase transition. And so you would say, well, you know, the CFTs that we are going to talk about actually 1 + 1 dimensional conformal field series. So why this is of relevance to condensed matter? Well, a lot of problems in condensed matter are actually problems of layers, right? So you're talking about theories on subtraces, and so those ones are relevant for the discussion here. Of course, conformal theories also show up in high dimensions as well. So we can have conformal gauge series, and they have interesting dynamics. So that's kind of motivation why we're talking about conformal field series. And the best thing of all is that usually conformal field series are solvable. Okay, and so a lot of things, including non-perturbative aspects, can be studied. All right. So having said this, we'll forget about string theory for now, And what we're going to do, we're going to have, if you wish, a mini course on conformal field theory. Actually, I want to give you some reference, which in particular will be for people who are interested in condensed matter. I find it's very, it's very good set of lecture notes which I used a long time ago. So those are lecture notes which is called applied CFT. Applied CFT, and it's written by Paul Ginsberg. And so it's a beautiful set of lecture notes where there's a discussion. It doesn't talk much. He doesn't talk much about string theory at all, if any. Okay. In a while since all right, guys. So let's get started.
Where are the notes published?
Okay, so if you Google, you will find them.
Okay.
And I think before he kept it on his website. I mean, if you will not find it, I definitely have it on my computer somewhere. So I'll send for those of you guys who want. It's actually very pedagogical, and there is a, it's I think one of the best notes I've seen and very accessible. But I think he actually later published it on FTH. This is lecture notes he gave at Harvard a long time ago. All right, guys. So CFTs. So the conformal series means that we're doing scalings, right? And series scale invariant, which means that it cannot have any mass terms. So what we're going to do, we're going to have our kind of toy model for a CFT that will start developing lots of techniques. And then at some stages, I'll just go into general discussion. So our toy model will be D massless scalars. In 2 dimensions. Okay, so this is our kind of model in which we're going to develop intuition about CFTs. I'm going to call it toy CFT. And so the action will take exactly, well, first of all, this is reminiscent to what is the theory on the string bullshit, right? So we have some massless scalars. So what I'm going to do, I'm just going to go ahead and just write down the action. Okay? And I'm going to write it down into sigma L1 mu. Okay, so what I did, you can say that I started with a Polyakov action. I choose a flat metric on a wall sheet, right? So this is Polyakov action. This is Polyakov action with kind of flat, so with a metric. So normally I would take eta AB for it to be flat, but actually what I did here, I did a rotation, so I did a weak rotation, and so my worksheet metric is just delta AB. So the theory is Euclidean, so I'm working with Euclidean field theory. Okay, so what we did here is a weak rotation. And so formally, so on the worksheet, I have 2 coordinates, sigma naught and sigma 1. So this is what we call tau. This is what we called sigma before. And so by weak rotation, what I mean is that I'm going into imaginary time. So weak rotation. So I'm going into sigma 2, sigma 1, where sigma 2 I define the I sigma 0. Okay. Right? A lot of things in the formal field series simplify if we go to complex variables. So let's go ahead and introduce it. I'm just going to introduce my complex coordinates. Z1 plus I2 bar sigma 2. And also instead of once I change to these coordinates, the real I have to define morphic. You hear me, guys? Yes. Okay, so we just started. You didn't miss much. Probably doesn't say good for me. 15 minutes, no information. So we started talking about Polyakov action, right? So I gave some general remarks why CFTs are interested. We started with the Polyakov action. We did a weak rotation, and we ended up with a Euclidean theory of massless scalars in flat 2 dimensions. All right? And what I'm doing right now is introducing complex coordinates because things, as we'll see, we're going to be much simpler. Okay, so del Z, which I also denote just simply by del, is 1/2 del 1 minus I del 2, and del bar, del over del bar, is a conjugate plus I del 2. And so the beauty of introducing derivatives in this way, because del of z equals 1, del bar of z equals to 0, and so on. Okay, so we went into complex variables, complex coordinates for our field series. So we can do exactly the same for any vector. So for example, if I have a vector quantity on a worldsheet, so I have 2 indices V1 and V2, I can go into holomorphic. So something that depends on Z, so Z holomorphic. And then bar anti-holomorphic. So we can go into holomorphic and anti-holomorphic indices by simply defining dz as v1 plus iv2 dz bar as v1 minus iv2. So those are just the definitions. Okay, so now what I did, I just changed variables, but the flat metric, which was delta AB, now I have to write down what the metric is in terms of this complex coordinates. So in this case, delta AB will go to G. So in general, I will have GZZ, GZ bar, Z bar, GZ, Z bar, GZ, Z bar. So that's our metric. And so if we follow through with the change of variables, how does our metric transform? So what we will find out, that those guys are 0, and this guy is 1/2 with our definitions. And so in particular, that means that if I raise the indices, right, for example, G Z bar equals to, obviously, there must be symmetrics. Anyway, so if I raise the indices, so raising the index, there will be a factor of 2. Okay, so very good. So now determinant of this metric, so it's Euclidean now, equals to 1/2. So if you follow through, and see how the area element transform, so we had before d sigma 1, d sigma 2, which is d2 sigma. So this guy transforms under this change of variables as implies d sigma 1, d sigma 2. And so what you see that the invariant area element stays unchanged. So this becomes the same as the d sigma.
Alex,
Yeah.
should it be minus g in?
No, because we did analytical continuation. So our signature is plus plus. Right? So this is what I mean here, deep rotation. So metric becomes plus 1, plus 1. And after that, we just go to complex coordinates.
So then just taking the determinant metric over there, you get 0 minus.
Yes. Yes. Yeah. So maybe yeah, you're right. Okay. So metric and one last thing. So I have to talk about delta function, right? So I'm going to define. Well, normally we define a delta function. So if I have d2 sigma delta 2, a delta function of sigma 1 and sigma 2. So we define delta functions in this manner. So the integral equals to 1. So now I want to define delta function in my complex coordinates in such a way that this integral equals to 1 as well. And so if you compare the two formulas, what you will find out that we relate this delta function as 1/2. Again, this is just a bunch of definitions. And then there is a divergence theorem that you guys have seen in complex variables. So that theory tells you that if I have an integral d2z of lz dz plus lz bar dz bar, so this I can convert the integral over a region as a contour integral. So it's going to be an integral around the boundary, and on the boundary we run counterclockwise. And so here I have boundary integral of this. Okay, so this is just a straightforward change of that. Okay, very good. So once we set up this new set of coordinates, we want to rewrite our action. And so it turns out that in above notations, our action will take form 1/2 pi alpha prime, and then I have an integral d2z del xu x mu. All right, guys, so any questions? Great, so now what I want to do, I want to find the equation of motion. Okay, so we want to extract equation of motion. So I vary with respect to x mu. So I'm going to get -2 over 2 pi alpha prime del bar of x mu. Right? Just stop. Yeah.
Wait, question. So d2z, it's dz.
Yes.
Dz bar.
So it's without anything. So this is the same as dz. So please, I'm I might be skipping some steps, so please stop me and we'll discuss. Okay. So the equation of motion implies that del bar of x mu equals 0. Okay, and so what do we find out from this equation of motion? So everything we do is classical analysis. Okay, so I can write this down as del bar over del x mu equals 0. So what this tells me? This tells me that del x mu. So remember that x mu on the complex coordinate is a function of z and z bar. And so the equation of motion tells me that actually del x mu is del x mu as a function of z only, right? So this equation of motion tells me that I have some function that is being annihilated by anti-holomorphic derivative, which means that it must be a holomorphic function. Okay. Holomorphic function. And also del bar of x mu is an anti-holomorphic. It can depend only on z bar. Again, because alternatively, I can write down this equation of motion as del over del bar. Okay. So any questions? No. Good. All right. So what we're going to do, we're going to use path integral formulas. And so in principle, again, what we can do, we can go back and quantize the CFT. And we pretty much did this in the Lightcon gauge in previous lectures. But what I want to do here is quantize it using path integral techniques and derive various word identities and Nilsson theorems using the path integral language. And that's what we're going to do now. So, okay, so let me remind you some useful relations in Euclidean path integral. So a path integral is an integral over fields, right? So I have an integral over fields. So now field series, the fields are dx. And so I have an action, e to the minus s. So that's a partition function of my system. And if I want to know what the expectation value of any operator, so if I have an operator, a curly f, and so this is some function of my fundamental fields, and I want to know what the expectation value of this operator is. So what I have to do, I have to evaluate this path integral where I insert the operator here. Okay. And actually, what I'm making an implicit assumption here. So I normalize. Strictly speaking, what I have to do, okay, I have to normalize it to a partition function without any insertion. So I would have to divide like this, but I'm going to set this to 1. Okay, so I want this is just a number. So I will assume that my partition function is properly normalized. Okay, so that's one way to so I want to actually say a couple more things here. So how do we think about this partition function? And how do we think about this expectation value? So you can think of this as what you are having. You are having an expectation value of an operator f, right, in a ground state of a system. So, but I want to point out that sometimes if I have multiple insertions, I can think about these multiple insertions as preparing a state for me. Okay? So how can I think of that? So I think it's easier. It's easier to so this is some insertion form. So if I have, for example, a product of two operators, so F1 X, Z1, Z1 bar, right, and then some other operator, F2. Let me actually have three operators. Okay. F2, bar. Okay, and so what I'm doing, I can insert this in a path integral. Okay, so x minus f. And so one way to interpret it, so I can interpret it as an expectation value of f1 f times f2, and this is an expectation value in the ground state. And I'm going to be a little bit sloppy here because we'll have more detailed discussion later. So there is an analog of a time ordering here, right? So in some sense, there is an order in which those insertions are done. But alternatively, I can think about what I want you to take from here is that I can think about path integral with multiple insertions as some insertions prepare me a state of the series. So alternatively, I can think of this as an expectation value of operator in this state. Okay, so there is a state, 2 and 1, where the state 2 in an operator formalism, you can think of this is that there is an operator F2 corresponding to insertions F2 that acts on the back. Okay, so there are various perspectives, and so very multiple insertions. If I have arbitrary insertions in my path integral, it means that I'm asking the question: what is the expectation value of a certain operator in arbitrary state? And the state will be defined by whatever kind of insertions I have there. Okay. This claim you can actually, so the best reference is the appendix of Joe Polchinski book. So he talks about path integrals in quantum mechanics, and so there is a detailed discussion there. But in some sense, you can think of this as rather intuitive, right? So, this is more or less clear to you, right? So what I'm having here, I can go, I can do mode expansion. So here I have an expression for operator F in terms of, say, creation and annihilation operator, if I were to talk about harmonic oscillator. And so now, if this operator is very complicated, for example, I have 10 creation operators. So instead of thinking that I compute an expectation value of operator involving 10 creation operators in the ground state, I can think that some of these operators act on a vacuum, and so they will create some excited state of my harmonic operator. And what is left there is an operator. And what I'm doing, I'm just measuring an expectation value of that operator in a state created by, by some path. So this is exactly equivalent to what I'm saying here. Is that more clear? And so again, the detailed discussion in the context of quantum mechanics is done in Polchinski book, and it's really the way. See, this is what I'm glossing over. So I have to introduce the notion of time ordering. So in some sense, since I have to prepare the state, so it must act before this operator acts, right? And so there is a notion of time ordering that enters. In fact, the correspondence between a path integral and an operator formally, what you naturally get here is not just the product of operators, but the time-ordered product of operators. And I'm assuming that you guys know Hess integrals. I mean, we don't go, I promise you that what we will need is not very complicated. At least I'll try to be intuitive. Okay, good. So any more questions? So there will be an analog of time ordering when we'll talk about radial quantization. Okay, so now there is additional relation that I want to point out. I'm going to call it a statement. So we know that dealing with boundary condition is very important. However, what I'm going to do, I'm going to be sloppy with boundary conditions now. And so in particular, I'm going to make the following statement. So this is a statement just in ordinary integrals. So if I compute an integral of a total derivative, so if I have something, so the integral of total derivative, I will say that this is 0. So this is a correct statement if I easily let the boundary terms, or the boundary terms are appropriately vanished, or like in a context of closed strings, if there is periodicity in the boundary direction. I'm always going to assume that if I have an integral of a total derivative, it just gives me 0. So, so this statement, formulated for simple integrals, has an extension to functional integrals as well. And so in particular, if I have a functional integral of the form, so I make a variation with respect to one field, with respect to field x of something, and by something, so this will be e to the minus, you can think of this as e to the minus s times something, it doesn't matter. The point is that this is the analog of the functional integral of the total derivative, and so it will vanish. And the way to, you can be rigorous again if you think about functional integral as infinite dimensional normal integrals. And so if you assume this, then you can show that this is true as well. Okay, so is it all right? So this is an important point. Okay? A lot of our discussion, a lot of things that we're going to play formally with functional integrals, and when we're going to derive various identities, will rely on this fact, okay? That the functional integral of the total derivative vanishes. Okay, so let's go ahead and find out the first consequence of that relation. Very good. So, so I have 0 equals a functional integral dx delta over x mu e to the minus x. Okay. So I'm looking at a specific example of the general vanishing theorem when my something is actually 1. Okay. So if I have that, so this becomes minus an integral of dx. And then I have e to the minus s delta s over delta x mu, right? And so this equals minus integral dx e to the minus s. And then the variation of the action we computed before, so it's minus 2 over 2 pi alpha prime delta bar of x. Okay. And so what you see, so I can write this down. I can write this down as my 2's will cancel. 1 over pi alpha prime And then I have a functional integral dx e to the minus x del del bar of x mu, which is the expectation value of del bar x mu. Okay. So what we showed that 0 equals to this expectation value, which means that the classical equation of motion that we derived there has to be understood as an operator statement. Okay. So why this has to be understood as an operator statement? So for now, I derived it as an expectation value in the ground state, right? But I can repeat exactly the same analysis by thinking that I have some additional insertions. So I take a derivative with respect that z bar, and so what I can think is that I have some additional insertion at some points that prime, and so as long as z is not equal to z prime, as long as those 2 points are different, then I can just repeat. I can repeat the same analysis, and I will find out that this expectation value is going to be equal in a state created by the insertion f. Okay, that's why I was going into the discussion that any additional stuff I can insert in a path integral, I can think of this as preparing me a state. So as long as those 2 points are different, so that my insertion, this z is not the same as the point where I insert my operator, then we find out that del bar of x equals to 0, which means that del over del bar x equals to 0 as an operator state. Okay. So is it clear?
Yes, just one question about this notation. When you put an f outside of the expectation value signs, when you say by...
Well, yeah, I didn't put it. I simply mean that, see, I'm going to say that the insertion here creates a state.
Right. I'm just wondering what the notation means. So when you put the f there, does that mean that the state on the right is prepared, but the one on the left is still...
Well, again, this f can be a product, right? So if I look at the expectation value in a diagonal state, then that f better be something times a conjugate operator, right? To be very... Okay, so if you want it to be completely precise, then this f must be something O diagonal times O. It must be a bilinear.
Right.
And
okay, so
then it will be very clear that one acts on the left, the other one acts on the right.
Okay.
So, but it's not, all those details can be worked out, and I just want you to have a, it's not important for me exactly how the state is created. Okay. The important part is that as long as those 2 points are different, this is an important thing, because see, when I take a functional derivative, I do not differentiate f. Okay? So that's why this difference is important. We will do our next example when we will be careful what will happen at the coincident points. Okay, and so we will see that at the coincident points. So this is an operator statement, right? So what we derive is that as long as those insertions are at different points, then as an operator statement, it vanishes, right? But and for me to get this result, I needed to show that whatever state I created, or whatever off-diagonal element, it doesn't. So from this perspective, it doesn't necessarily have to be in this form. So you can think that it acts on the, on the vacuum on the right, and there is a vacuum on the left. Okay, good. Yeah.
What will be the boundary terms for the functional integral in general?
In general, so again, in our case, for the closed strings, there will be none, because it's going to be periodic. Normally, when people talk about quantum field theories, we make an implicit assumption that boundary terms vanish. So the way we are achieving this by assuming that the fields die off as we go to infinity in the field space. Okay.
So how they look like? So this boundary term just field on the.
Well, the boundary term, you know what it will be.
Can you
Right?
explicitly?
No, it's exactly like it is here, right? So if I have this integral from A to B, you know that this integral is something, whatever I have evaluated at A and B, right? It's exactly the same going to be here. I have this expression, so that's some functional depends on the field, and I have to evaluate it as
fields.
in the field space, right?
Mhm.
So here A and B are just some numbers. So here B will be the value of the field at plus infinity, and so clearly, at least in this simple scalar field theory, as long as I have e to the minus s, that will always be the case. Because if I go far away in the field space, and well, unless I'm looking at zero modes, as long as del x is not zero, then you have a suppression for large values, right? Because s, well, in the Lagrangian, right? Well, I can write down 2 pi alpha prime e to z of del x absolute value squared, right? So as long as I'm not at the zero mode of the field, meaning that del x is not equal to 0, then the action becomes infinitely large as I go to large values, right? So, but in the Hess integral, it always enters e to the minus s. So you have always a suppression. But again, sometimes you have to worry about boundary terms, and it depends on the problem. Okay, so that you have to deal with. So it's citation for everything we're going to discuss in this course to assume that we forget about boundary. Okay? And I gave you kind of semi-hand waving arguments why we can do so. Okay, so let's go ahead. So as you can see, I've been a little bit sloppy here, right? So I told you that well, I keep saying as long as the 2 points do not coincide. So let's be a bit more careful and see what will happen if we take care of a possible point collision there, right? So the next example is going to be the following one. So I have 0 dx, and then I have delta over delta x mu z and far. So here I have e to the minus s, and so I will take a very specific form. I will take a very specific form of my operator f there. I'm going to take it x mu that depends on z prime bar. Okay. So I still have a 0, right? The reason why I have 0 is because it's a functional integral of the total derivative. And now I have to compute carefully functional derivative. So when I differentiate e to the minus s dx, I will get e to the minus s, right? And then I have minus 1 from here, and then I have a functional derivative of s with respect to delta x mu. So that gives me 1 over pi alpha prime times del bar of x mu, and there will be additional minus sign, so altogether I will have a minus 1 squared. Okay. This is just literally repeating what we have there. So that's one term, and then there is another term. And so the other term, when I act with the functional derivative on this insertion. So I will have e to the minus s, and then a functional derivative delta x nu of z prime z bar prime over delta x nu of z bar. Okay. So now I have been careful, and for now I'm not talking about any additional insertions, right? So what this is, right? So first of all, this guy is just delta nu nu. Okay. So the indices must be the same for that functional derivative not to vanish. And then in general, those two functions are at different points. So if I differentiate one with respect to another, I will get a delta function, and the argument of a delta function will be that prime bar. Okay. So yes.
In the first term, shouldn't there be an extra factor of x mu?
Oh yes, sorry, of course. Yes. So there is an x mu. Yes. Okay. Okay, very good. And this guy acts on that. Okay, so now notice that all of these guys come with come with e to the minus s. So the first thing is an expectation value of the Fourier type. So I have del z, del bar of z, okay? And what I have here is, all right, so the index here must be lower because I differentiate with the upper. So I'm going to put a lower index here. I want to keep an upper index here as well. So, and then this guy will be just eta union, okay? Are you all right, guys? Yes?
I'm not sure about x nu.
Sorry?
Why x nu is there?
Why x nu here?
Yes.
Oh, because here, this term here obtained when I add with this derivative on e to the minus s. It's just I differentiate the product of the functional, right? So this goes along. Now here, this goes along, but I differentiate here. Okay? So the first one, these guys act on z, and this guy depends on z prime. So I have del z, del bar z. And then here I have an expectation value of x nu of z bar, x nu of z prime, z bar prime. Okay? And the other piece is just the expectation value of the delta function, right? Plus eta mu, the expectation value of the delta function. Okay. So what we showed, so now you can see is that we get our previous result, that the equation of motion agrees as an operator statement ground state as long as insertion points are different. However, and I can now repeat the same kind of dance that I did before, saying that, well, I can insert any additional operators, and as long as they are not at z or z prime, so I'm going to make, we're finding the following equation of motion. 1 over pi alpha prime del z bar x mu of z. Okay, I'm not going to write down. Sometimes, guys, I don't mean that x mu is holomorphic, but I'm going to skip sometimes their bar dependence. Is that okay? It should be obvious from the context. So I should not distort. Yeah. And then x mu z prime z bar prime. So here equals to minus 8 mu delta 2 z and z prime. Okay, so we found a modified equation of motion that takes into account that there is a collision between point z and z prime, so again, I can derive this as an operator statement because I can prepare arbitrary state as long as it doesn't coincide with point z and z prime. Okay, and from this type of analysis, you can see what will happen if points z and z prime will coincide with some additional insertions. You will have additional singularities, and those will be similar to the singularities we found here. Those would be a delta function like singularities at the insertions. But the equation of motion will be preserved away from the insertions. Okay, so any questions? No. Good. So now I'm going to make a very important, introduce an important notion, and that's going to be a notion of normal ordering. Okay. So remember that what we found that del over del bar of x mu classically equals to 0. Okay, so we found that the equation of motion is very simple classically, but quantum mechanically, and I emphasize that right now all these identities that we derive, say quantum mechanically, including all possible fluctuations, the reason because we derive them using a Passe integral. Passe integral includes all possible quantum corrections. So what we are finding is that so del over del bar x mu quantumly is not equal to 0, and there are these delta function singularities. And so what we want to do, we want to define in particular product of operators that would satisfy the naive classical equation of motion. So let me illustrate it with product of two operators that we discussed before. So if I have two operators, x mu of z1 and z1 bar, x mu z2 z2 bar. So classically del 1 bar. So classically it's vanished, but quantum mechanically it's not, and it has this additional delta function, right? So this is minus pi alpha prime times beta mu delta function z1 2. Okay, so where z1 2 is just the difference between 2 points. And so you can see that the equation of motion satisfied that the product of two operators satisfied differs from the classical equation of motion. So we found this is quantum correction to classical equations of motion. Okay, so is that clear? So now what I want to do, I want to define, so here I have a product of operators, right? I want to define a product of operators in such a way that it satisfies the naive classical equation of motion. So I'm going to denote the product of two operators. So I'm going to call it the normal ordering product. And so, so I want to define this. Okay. So what we want to do, we want to define what we mean by these dots. So this is a definition. We're going to define it in such a way that del 1 bar, so it gives me 0. Okay. You can see that in some sense, normal ordering of operators behaves exactly the same way as classical fields. Okay. So how do we achieve this? Well, it's obvious what we have to do. We know this exact quantum equation of motion. And so this tells us that we need to define it in such a way that we will cancel this piece. So I'm going to make a claim, and then I'm going to prove this. How exactly we do this definition. It turns out that the words for sure you have heard before, but I'm not sure that you have seen this in this particular context. So I'm going to define a normal ordering of two operators. I'm going to define as follows. Well, a normal ordering of a single field is just the field itself. Okay? And if I have two operators, x mu, I'm going to define a normal ordering. So there is no normal ordering, something that we know how to deal with. The reason why I'm saying we know how to deal with is that I think of this operator as an insertion in a path integral, right? So all I have to do, I just have to take two fields and insert in path integral and compute the resultant functional integral. So I'm going to say that the normal ordering is what is normal ordering, and then there is additional term, and this additional term is alpha prime over 2 eta mu log absolute value z12 squared. Okay. So again, this is a definition, and what I'm going to show to you now that when I define my normal ordering in this way, then the equation of motion, that the product of operators satisfies the same as a classical equation of motion. Okay. So is the logic clear? You know, you used to think about normal ordering when you go into oscillator basis, right? And you write down all annihilation operators before the creation operators. You call that normal ordering. That's what we call normal ordering. So this is a more conceptual way of thinking about normal ordering. Okay? So again, we're still here in a free field series. And the idea of normal ordering is to think about composite operators. Operators that are k when we multiply fundamental fields. And the idea of normal ordering is so that there are no quantum corrections. We're kind of removing quantum correction from composite operators. So why am I saying that that's a good definition? The reason for that is that now if I act on a normal product, right? So what do I have? So the first piece gives me minus pi alpha prime, right, times eta mu. And then I have delta function of z12, right? So it's just following the equation of motions that we derived before for normal operators. And then I have to take a second derivative of this law. So I have alpha prime over 2 eta mu L1 bar of log absolute value squared of z1 bar. So I'm going to show you that this guy is actually a delta function, and it comes up with the right coefficient, so everything is cancelled. So let me show this. So this is because, and this is going to be 0 because del over del bar log absolute value of z squared. I'm going to show you that that's 2 pi times the delta function, right? So notice that if that guy is 2 pi times delta function, so you have 1/2, so you will have pi, which will cancel precisely the first term. Okay? So why this is true? Well, okay, so proof. Well, so first of all, suppose that z is not equal to 0. I'm claiming that this is correct for any values of z. So if z is not equal to 0, then we have del bar of log z plus log of z bar. Okay? So this one is holomorphic function, this one is anti-holomorphic function, but I add both with holomorphic and anti-holomorphic derivative. So this guy is 0. Okay, so as long as that is not at 0, then this derivative is 0, which is exactly the same as the delta function. So if I am away from the 0, the delta function is 0. Okay? So there is an agreement, and so the only thing I have to check whether the relation agrees exactly at the point that equals to 0. And so in order to do that, because if I expect that that's a delta function, the way to test whether the strength of the delta function is the right one, I have to integrate both sides. So that's what we're going to do. I'm just going to compute an integral of d to z of del bar log absolute value of z squared. Okay? So this is left-hand side. And the right-hand side is going to be equal an integral of 2 pi delta 2 d to z. It's going to be equal to pi. Because the way we defined our delta function is that the integral of delta function equals to 1. Okay, so let's go ahead and compute the left-hand side. So I can think of this. As an integral of d to z of del z of dz. Okay, and so dz is just del bar of log absolute value of z squared. Okay. So I just broke the integral that had 2 differentials, del bar. I just said that I'm going to write it down as del z acted on the vector dz, and dz is given by del bar log of z plus log of z bar. Okay, so I can compute that this derivative, so this is the same as 1 over z bar. Okay, so we are finding that this left-hand side equals to d to z, del z of dz. And then here comes a beautiful thing. Remember that I wrote you divergence theorem somewhere in the blackboard. How do I translate the integral into an integral on a contour? And so here I can assume that I'm integrating inside the disk. Okay, so then there is a well-defined boundary here. Okay, so I'm integrating inside the disk. And the reason is that, well, we already showed that this identity holds true for any z that's not 0. So now, if I use divergence theorem, then I can write this down as an integral over the boundary. The boundary is absolute value of z equals to 1. And so it's going to be equal to dz bar. Okay, so if you go back and look at the divergent formula, and there will be no other pieces. So this is going to be, is it okay if I continue writing? It's not okay, I know. I kind of ran out of space, right? So this is an integral of dz bar over z bar. Okay? Now, the integral dz bar over z bar is a complex conjugate of 2 pi r, right? So I have pi times 2 pi r, complex conjugate. And so what we found that the left-hand side equals to 2 pi, exactly the same as the right-hand side. Okay?
I have a question.
Yes.
AZ is equal to 1 over the bar. This result just is right only for z, and z is not equal to 0.
Right.
Because z and z bar.
Yeah. Okay. Okay. I see where you are heading. Right. So, so you're saying that because z is a complex variable, right? Z and z bar are not independent, right? Because once I know what z is, I can figure out what the z bar is. Just take a conjugate, which is correct, right? So notice that we are in 2 dimensions. So we had sigma 1 and sigma 2. So we had 2 coordinates. So in principle, they are related, but I don't have to make. I can think of them as being independent. Okay. The reason why am I doing that is because we already saw that some of the fields depend only on that and not on that bar. So I can use the theory of complex analysis, which is something what they used here. So in writing all these formulas, I didn't mention this. I'm thinking that that and that bar are independent. Okay. Which is also the way, if you think how we are writing the areas and integrals, right? So I'm thinking when I write down the metric, and metric has a component that's that bar, I'm assuming that those two are independent. That's a good point. All right, guys. So is this technicality clear? Okay. So now let's go through track of the general discussion. So the general logic is this introduction of the normal ordering, and what we showed is that if we modify a product of two operators by adding this constant piece, which is just a log function, then what we are finding is that there is the composite operator satisfies the equation of motion for the classical fields corresponding to those operators. Okay, so good. So I guess I want to make this point here as well. So typically in quantum field theory, when the operators coincide, there are singularities, right? And so we saw that that's even true in free field theory, right? So when we take a product of two operators, there is a singularity exactly when they coincide. And this singularity is governed by this log function. So what we did, we actually redefined a product of operators in such a way that there are no singularities anymore at one of them. So that's been done in a free theory. So it is possible to do always when there are no interactions. So if there are interactions, the normal ordering is not very useful because there will be additional divergences in the composite operators. And well, I mean, it's not to say that it's not being useful, but I guess I want to say that in the composite operators, if the theory is interacting, there will be additional divergences which you would not be able to remove in a similar uniform manner. All right. So now I want to go into some discussion that we, when you read Polchinski's book, he just mentions this, but it wasn't clear, at least to me, when I was reading it first time. So what is the meaning of this? What is the meaning of this operator product expansion, right? So I can think that I have a complex plane. Well, you can think that I put a boundary someplace. And so what I'm doing, I'm inserting two operators, one at that one, the other one at that two. Okay, so here what we did, we inserted x mu, and what we did here, we inserted x nu, and then we derived some normal ordering product, right? So we defined some normal ordering of this operator. Now remember that I will keep saying words as long as there are no other insertions in the path integral. We always have to think of this as an operator representation of matrix elements that we obtain in a path integral. So what this means that inside, so if I make a circle around that one, then inside this circle there are no more insertions, right? So there can be additional states, additional operators that are inserted in a path integral, but they are outside this shaded region. Okay. So it is in this sense that you have to think about this normal ordering. Of course, if I start taking into account additional insertions, there will be additional singularities there, and it's clear a way how we can extract that. So there will be a similar procedure. We actually formalize it in a second in general. But is what I'm saying understandable? Okay. Right. So the reason I'm talking about this is because we're going to introduce now the concept of operator product expansion, and it's a very powerful tool in conformal field series. The reason, and I'll explain the reason in a second, right? Well, first of all, in a string theory and in a conformal field theory, what are the observables? What do we compute in our field theory? Well, we compute a set of correlation functions of some local operators, right? So I have, say, n local operators at some insertion points. And I want to know what is this correlation function. So when we take Polyakov action and we compute the correlation function for the conformal field theory coming from the Polyakov action, then we show that this correlation function will be related to a scattering amplitude in the 26-dimensional space. But that's running way ahead. It's just as a motivation why we want to do it. But you can forget in a conformal field theory, if you do condensed matter or something like that, that's exactly the stuff that you are interested in. So you are looking at some critical behavior in the system. You look at the correlation function, and you see 7 critical exponents. So what you are doing, you are computing correlation functions. So these correlation functions are observables. Right? So normally when we talk about, say, quantum field theory, the observable are the scattering amplitudes, right? So we can construct asymptotic states. So when we talk about conformal field theory, the proper way to think about observables is not the scattering states. One of the reasons is because they are not defined in a complicated CFTs. And so the right way to think in terms of correlation functions. And so in fact, later we will see that we will be interested in the behavior of these correlation functions as Zij goes to 0. So we will be interested in the singular behavior of the correlation functions. So in fact, the singularities in the correlation function, they encode information, what are the physical degrees of freedom in exterior. Those are like poles in the propagators, right? So interested in singularities. For more general interest, we will be interested in how the correlation function behaves when some of the points coincide. That's in some sense exactly what we were discussing here, right? So we had 2 operators, and we get this interesting log behavior because we wanted to know exactly what will happen with the product of these 2 operators as one point approaches the other, and we found that logarithmic singularity. So the technique, the formal way of asking this question is to talk about operator product expansion for OPEs. So the notion of OPEs is the following. So the idea is, let's look at 2 operators, sigma 1, Aj, sigma 2. So what we want to do, we want to think about, if you wish, a complete set of operators. And so when I have a product of operators, I think about this as an algebra. I can write down as an expansion in terms of my basis operator. So I want to write this down as a sum of the coefficients k, ci, j, k. And so here, sigma 1 minus sigma 2. And then here is ak of sigma 2 dots. So what I mean by this is actually this. So I have a correlation function. I don't know why I switched from Z to sigmas. But anyway, so I have two operators, and I expand them in a complete set, and those are the coefficients of the expansion, right? So, so these two operators, right? I expand it as an infinite sum of my operators a sub k, so those are the coefficients of the OPEs. So what is typically happening? So typically, what's typically happening is that those coefficients, there is a natural hierarchy, and so there is a natural way in which this coefficient Cij is proportional to sigma 1, 2 to the power k, right? So there is kind of a Taylor series expansion when two operators approach to one another. In normal quantum field series, this Taylor series expansion almost always has zero radius of convergence. Okay? So, so in normal QFTs, so this series expansion, radius of convergence is 0. Okay, so that's not bad. There are lots of series in quantum field series which are just asymptotic series, and we can live with them. However, conformal field series are very special. In a conformal field series, this type of operator product expansions are actually have finite radius of convergence. Okay, so in CFTs, OPEs have finite radius of convergence. Okay, and the reason, sort of intuitive reason why that is happening is that we have singularities only at the when different insertions coincide. So as long as, for example, if I look at OPs of two operators, O of Z1 bar, Z1 O2 of Z2 Z2 bar, and I want to write it down. I want to write it down as an expansion in terms of some complete set of operators. And we will later today hopefully define what are this basic set of operators in the CFTs that we're doing this type of expansion. So this is, again, just rewriting C1, 2, K, OK of Z2. So these guys is the functions of Z1, 2. So this series, so this is an infinite series, so it has finite radius of convergence. And so if I have Z1 and Z2, and so there is some third operator, so this is O1, O2, O3, which is inserted to a point 3. So the radius of convergence is the distance to the next insertion, right? So it's kind of very similar when we were deriving the equations of motion, and those equations of motion had a single logarithmic piece and nothing else. And the reason for that is because we were assuming that everything else has been inserted outside that one and that two. So this is our radius of convergence. So this is going to be radius of convergence of O1, O2, O3. move, we say one move, and then I ask. So again, the situation is very similar when you deal with series of complex variables, right? So there will be different pole singularities. And in a series of complex variables, what happens is that typically their radii of convergence are finite, and the radius of convergence is just the distance to the next singularity. So you can think of this that when we are computing products of operators or correlation functions, it's kind of similar to inserting singularities in the language of complex analysis. And so the radius of convergence will always be the distance to the nearest singularity, other than the one that you take into account. See, in some sense, what we are doing, we are taking into account this singularity by writing down this complete series expansion, but we are completely forgetting about this singularity. So the radius of convergence is determined as the distance to a nearest singularity, which we did not take into account. Okay, and so that's actually the underlying reason why the OPEs that we will derive will always have this finite radius of convergence. I have to say one more that, of course, this insertion will depend what state you're preparing, right? So whether this additional operator is, whether this additional insertion is, depends on what state you're looking at. So when you compute some specific correlation function, you always have to care whether there are any insertions, whether the state that you compute the correlation function does not produce singularity which you didn't account for.
Okay. I have a question about the expansion itself. So,
Yeah.
I'm not really sure what goes in the expectation value symbols that you have on the left hand and the right hand side. So on the left hand, I think I'm pretty clear. You just have a whole bunch of
Operators that I take into account only two, and the other ones are outside that one and that two. Right? So,
Okay.
so it's really this picture. I look at this, and then there can be other operators, but they are outside.
Okay, great. And now on the right hand
So on the
side,
right hand side, what I am doing is that I'm saying I don't want to deal with composite operators. I want to say that I have some well-defined basis of operators, which we will find out there is called chiral, that we will call primary operators or tensor operators. We'll define exactly what they are. But those are like your basis in this operator space. And what I'm saying is that whenever I have a product of two operators, I'm going to expand it in this basis set of operators, right? And those guys are the coefficients. So this is an operator, but those are just the numbers, the coefficients. They depend on the distance at which I expand this, at which I insert these two operators. Right?
okay.
And the point is that you can think of this as a Taylor series expansion because, and we will see specific example, what will come up that if it is, you look at the coefficient with index k, it will go as sigma 1, 2 to the power of k. It's really like an expansion in terms of proximity. Right? So the small parameter is the distance between two operators. So you kind of ask the question, okay, I have these two operators which approach one another, and I want to know what are, if I think of this as there is a well-defined basis of operators, what are the most important operators that govern the singularity? Okay? So those would be like the first two terms in this expansion, or the first couple of terms in the expansion. Okay?
Okay. So in the expectation values on the right hand side, do AI and HA appear? They don't. Right?
No. See, they are already now in this index coefficient. So the index I and j is simply what I'm doing. I'm taking two operators, and I crunch my machine and ask, what are the coordinates in my basis? Those coordinates are given by this function, right?
Okay. So in the case where you only had three operators on the left hand side,
Yeah.
right? On the right hand side, you would
So
only
this
have
is B.
yeah. Then you would. I see. So the B is still there. I thought the B would be the AK.
No. All I'm doing is that the dots means that I have additional insertion. I have additional set of operators. And I'm asking the question, of course I can ask more interesting question in which what will happen when three operators collide. So some more complicated question and more complicated type of singularity. But I'm asking about simpler type of singularities that happen in correlation functions only when two operators coincide. So this B is kind of analogous of my operator O3. This is my B, right? So it's outside. I don't allow it to collide. Okay? All right? Right, guys? Let's keep moving. And good. So now I'm going to prove to you. So now we go into one very specific example, and you will see exactly how this operator product expansion works. Okay. So let's go back to the examples that we discussed earlier today. So we derive with use this beautiful identity that if I have del 1 bar acted on x mu of 1, x mu of 2, so this guy equals to 0, right? So we defined our normal ordering in such a way that it satisfies this equation of motion. So, but this is the simplest example when I have two operators, right? One is at point z1, the other one is at point z2. So now let's see what this means. So what I can do, I can think of it this way. L1 z bar of x mu equals to 0, right? And so L1 bar of L1 of L mu equals to 0. Right? So I haven't done anything, just a little in a silly manner 3 times. Actually, it's important what I did, because what you see is that so this guy is anti-holomorphic derivative, and this guy is being annihilated by anti-holomorphic derivative. What this tells me? This tells me that del 1 of x mu of z1 bar, and then of z2 bar. So so as an operator, this is a holomorphic expression. Is holomorphic. Okay, so it's a holomorphic function, and so what this means that I can just Taylor expand it. The theory of complex analysis tells me if I have a holomorphic function, it has a well-defined Taylor series expansion. So, so what I can do, I can think of this is that this is the derivative of del psi, and then x, well, okay, I don't know how to write it down in a good way. I'm going to do psi, that's 2 bar, psi bar. Okay, where psi is just z1, 2, the difference between z1 and z2. And so the theory of complex variables simply tells me that if I have a holomorphic function, it must be a Taylor series expansion. Right? So I can write this down as an infinite series. So this is sum k equal 1 to infinity psi to the k over k factorial, and then I have x mu. Okay, and then I need to take k derivative. So this will be del k of x. Okay, there will be only holomorphic derivatives because this function is holomorphic. Okay. So the important thing here, we're going to write down one more line, and then we need to talk about that. So then, so I can realize this is sum a equals 1 to infinity, z1, 2 to the power of k, and then I have x mu of z2, z2 bar, and then del k x mu of z2, z2 bar. Okay. So notice what I did. So I did a complete Taylor series expansion, right? So this guy depended on Z1, but I now wrote it just as a function of Z2. Okay. Only. So so what this tells me. This tells me that if I have a normal ordered product Z1, Z1 bar, x mu of Z1, sorry, Z2, Z2 bar, right? So we showed that this is the same as a normal order of x mu of Z1, sorry, Z2, Z2 bar, x mu, Z2 bar. And then there will be an infinite sum. So we looked only at the holomorphic piece, but then there is I can repeat everything in a similar fashion because I can write down here as del one bar of x mu equals to 0, and so this is an anti-holomorphic function. So if I do it in general, then there will be two infinite series, right? So the first one is like this. So cross sum a equals 1 to infinity. That one to k over k factorial x mu del k x mu normal order plus z1 to bar k over k factorial normal order x mu del bar x mu. Okay. So before we go, I will say some words why this is a OPE. Okay, but before we go there, is there at least the algebra clear? Okay. Is it clear what manipulations I did? We'll talk about physics in a second.
Why the partial operator can compute with normal ordering? The identity.
Well, it depends on that's the only thing that depends on that one, so I can just insert things in. I mean, in some sense, normal ordering is something that makes things classical. That's, I guess, the easiest thing to think about. See, you used to think that when you have a product of operators, and you have to be, especially if there is a time ordering that's naturally come, there will be delta functions that come because of the time ordering. So the analog of those time ordering delta functions in that formalism, right, are the delta functions that we see here at the insertions. Okay, but right. So what I am saying here, okay, so why this is an example of OPE. What we just discussed with you is the simplest example of OPE, because what we had two operators. One operator was at point Z1, and another operator was at point Z2. And so what we did, we wrote the product of these two operators as an infinite sum of some coefficients, right? C sub k of some operators, some basis operators, A sub k, right? that we're living at local operators, right? So the important thing here is that we have product of operators at different insertion points, but we want to write it down as an infinite set of operators inserted at the same point, right? So here I have, I choose the point Z2, and so if you compare what we have done here, so this is the analog of our x nu, this is equivalent to our x nu. So the operators that form the basis here for the expansion of this product are actually the operators of the phi x nu del k x nu, right? And then there is x nu del bar k x nu, right? So a set of these operators, they carry index k. Those are the operators that enter into the expansion. And the coefficients of the expansion is just Z12 to the power k over k factorial, right? That's exactly what we derived. So what we showed is that if we take two fields at a different point, as long as those points are close enough, and close enough meaning that there is no additional operator inside Z1, Z2 circle, right? So this, again, if you remember how we derived that relation, so this is only true if I have Z1 and Z2, right? So as long as there is nothing else inside this shaded region, then this series has converges, right? And what we achieved, instead of thinking operators at a different point, we represented it as a sum of operators which lead just at a single point. Okay. So is the logic clear?
But this AK is still a product of two operators. X nu,
No,
X
no,
n.
it is. Yeah. So it's not. It's That's why I use a different letter here, right? So the basic operator is not necessarily has a simple expression in terms of fundamental keys. So it's a composite operator here, right? So and in fact, so in this particular case, that's a composite operator defined with normal ordering. So they are almost like a classical operator. Well, they behave like classical, the product of classical fields in free series. Yeah, but you're absolutely right. So those operators are not supposed to be simple, right? So in this case, you can see that there is an infinite set of this complicated operator. And for now, it's not clear what is the organization of how do we organize, how do we come up with a basic set of useful operators. And I promise you that we will. And there will be a nice simple classification how we do that. All right, guys, so any questions? That's our first OPEs. Okay. Good. So so what we did before, we did normal ordering when I have two operators, but it's clear that I can extend it to an infinite set of operators. So I'm just going to write down the three operators. And I'm going to now put it in the language that you have heard before. So, for example, suppose I have three operators. That one, actually n operators. I decided to go n, x mu n, z n, z bar n, right? And so, again, the way we define normal ordering in such a way that the product of operators satisfies the normal equation of motion. Sorry, the classical equation of motion. So this product here is a product where I'm not doing normal ordering. Plus sum of subtractions. So this is this is really should ring a bell for you. How you define a normal ordering when you have products or fields? So you replace, you go from a say time ordered product, you go to a normal ordering product plus a bunch of subtraction. So plus subtraction. And the subtraction, so what is the subtraction? So what we have to do for a subtraction, so we take a pair of operators, and well, I mean, subtraction calls contractions. I think I've seen this word also in here keys. So the subtraction is contraction of a pair of two fields, or what we do, we're going to replace a pair of fields. We have to replace a pair of fields with 1/2 alpha times eta ui uj log absolute value z ij. Okay. And in order to derive this, the derivation is equivalent to what we did with just two operators, right? So all I have to do is I have to write down, for example, I have to write down is dx delta or delta x u1 z1 z1 law, and then e to the minus s, and then here I have u2, that's 2, that's 1, x un. Okay? I'm just going to write down the same identity that functional integral of the total derivative is 0. And then when I'm going to take functional integrals, the first piece will come from here, and it will give me this term, right? And then I have this functional derivative that will act on these operators, and that's what will produce subtractions, right? Each time I take this, I take this functional derivative, it will produce a delta function. And in the equations of motions, it will produce for us this logarithmic dependence. Okay? So is that obvious? Okay, there are two reasons why I'm not going to do it. The first reason is that it's too long to write, and it's really just repeating the same steps what we did in for just a single operator, right? Then here I have n minus 1 here, right? N minus 1 field. So when we do that for two fields, I have x mu1, x mu2. That's what we derived before. It's x mu1, x mu2 plus a single subtraction. Okay, and so it's obvious that nothing other than pairs will come up in this discussion, right? Because when I take functional derivatives, there are only delta functions that will come out, and the delta functions will show up as this logarithmic singularity that I'm writing down equations of motion. Okay, guys, so let me do a couple more things, and after that we'll take a break, okay? And that will be, after the break, we will actually do a bunch of examples and compute normal ordering for some interesting operators that we will use later. So, so good. So I gave you the rules of the game, right? So if you have a product of operators, in order to construct a normal ordering, you take the product and then you choose pairs of fields and you replace pairs of fields with that log times eta mu. Okay. So there is a generalization of this. What do I do if I have, for example, a complicated f? Okay, so f is my arbitrary operator now. It's a functional. So it depends on lots of fields, right? So u1, whatever, you know, x mu n at different insertions. It can depend on derivatives of the field, so on, some very complicated functional. And what I want to do, so this is a combination of fields, right? Like I would do for the classical fields. I want to write down the analog as a normal ordering. So what's the normal ordering of f? Okay. Well, so the idea would be take this horrible expression, expand it as a Taylor series, make it as an expansion that involves polynomials of x, and then write down a normal ordering for each monomial in this infinite series expansion, right? And for each monomial, we know what we have to do, right? So whenever we see a product of two fields, in order to go to normal ordering, we have to add a subtraction term. So you can convince yourself, again, I'm not going to derive this, but it's kind of straightforward, that to go to a normal ordering, you have to act with exponential derivative, and so this exponential derivative is alpha prime over 4, and integral d2z1, d2z2. I'm not going to explain it, but I'm going to explain one number, it's an expression. And then I have log, absolute value z1, z2 squared, and then the functional derivative of x mu of z1 bar, delta of x mu, z2 bar. So this functional derivative acts on f. Okay, so what I did, I exponentiated the derivative, and then I make a claim that a normal ordering of any functional is that complicated derivative acted on f. By the way, do you guys know what I mean when I write down e to the del? Yes? Okay, so yes or no?
E to the del?
Yeah, del over del x. What do I mean? I mean, I'm assuming that, okay, you either understand it or you don't. And if you don't, that's not good, because since you're not asking the question, it means that you are not hearing. So what do I mean by e to the del over del x, right? Is it clear what I mean by that? Exactly. Good. So you're on much better side. So what I mean here is Taylor series expand, and then act with this functional derivative. And so logically, why this formula is plausible, right? So once you have something like a product of x's, so every time you do the expansion, you act with two derivatives. So you kill two x's, right, in the product of x's. But then you kill two x's by derivative, and instead of x's, you insert log z1 2 squared, right? So that's exactly what this subtraction is doing. Okay, to go from the not normal ordered stuff to normal ordered stuff, you'll just add this subtraction. Okay, is it clear that it will do roughly this? What I'm going to explain to you is, I told you I'm going to explain one number. I'm going to explain that 4 here, right? So you can see that in the subtraction there is 1/2, but somehow in this exponential there is a quarter. So why there is a quarter? You know why there is a quarter? Because a quarter is 2 times 1/2. And 1/2 is a symmetry factor, because when I act on the first x, I can act with either with the first derivative or with the second one. Meaning that either with the one involving z1 or involving z2, and everything is symmetric. So there is just this symmetry factor. Okay, good. So now we know that if you give me any functional, I can construct the normal ordering functional by simply acting with that complicated derivative. And now I'm going to write down two more formulas. Of course, if I have that relation, I can invert it, right? So I can write it down that the operator without normal ordering is exponential to the minus alpha prime over 4 d2z1 d2z2 delta over delta x mu 1 delta 2 and this acts in function, which is again a simple statement that I can put this fraction on this side, and then it will be a relation between standard product of operators and product of operators involving normal ordering. And so if we expand this, right? So in this exponential, there will be just this stuff plus sum over contractions. Okay, so there, people call it subtractions, right? When we go from normal order to a product of operators. So here, people, including Jopolchinsky, call it contractions. And you know that what contraction is? It's simply minus 1/2 alpha prime eta mu log z1. Okay, so it's just opposite. Again, the follower here is simply inverting this relation, moving subtraction on the other side and calling them contractions. Okay, so that's why there is a minus. Not very deep. But now the last step in this language is so again. So in general, we have we know that ultimately we want to deal with normal ordering of operators because it is normal ordering that has simple classical equations of motion. But when we take a product of operators, how do we rewrite a product in a normal ordered form? So my last formula is going to be the following. So suppose I have a product of two normal ordering operators, right? And so so I want to write down. So those are complicated functionals along the lines that we discussed there. So I want to write it down as a normal ordering of f and g, right? So what I would do, I would write down if it wouldn't have any of this, then it will be normal ordering plus contractions. But I actually there is a partial normal ordering, if you wish, here. So instead of full contractions, there is here a summation of cross contractions. Okay, and I'm just going to explain what exactly these cross contractions are. So, so in the language of that complicated functional derivative, what this guy is. So, so this is exponential, right? So for the full contractions, I should have minus alpha prime over 4. So now I'm going to say that there is minus alpha prime over 2. I'm going to explain, of course, only this 2. An integral of d2z1, d2z2, log f of w z1 squared. And now I have delta x mu f of z1 bar delta of delta x mu an additional subscript g z2 bar. Okay, and this whole guy acts on normal ordering of f and g. So everything as before, except that now, before this functional derivatives del del x acted on any of the fields, right? So here I am putting a subscript f, meaning that del over del x acts only on f, and this guy del over del x subscript g, it can act only on the fields inside the g function. It is precisely for this reason that the factor of 4 there became a factor of 2. The reason is there we needed a factor of 2 because there was a symmetry. Each of these del's can act on the same field x inside f. But now we don't have that, okay? And so you can see that that's the reason why it's called cross contraction, because it will bring in this log of z1, z2 when I contract one of the fields in F with one of the fields in G. Okay? So is it, I wouldn't say obvious, but is it reasonable that if you expand it, that's the way how it will work? Very intuitive. All right, guys? No questions about this. So what we're going to do after the break, we're going to look at a bunch of examples, and we're going to compute exactly this identity. The reason why we're going to do that is because that will help us later when we discuss the stress energy tensor conformal field theories. Lots of computations we do now will just go over. All right, so let's make it 10 minutes.